Hello, everyone. Thank you for listening in. This is Group 23, and we're going to be presenting on our project. We worked on disposable bioreactor seed train optimization.
Antibodies are biological molecules found in our own bodies, which can effectively treat numerous diseases, including rheumatoid arthritis, multiple sclerosis, cardiovascular disease, and even various forms of cancer. Antibodies are also a high-value therapeutic, with 7 of the top 20 selling drugs worldwide being therapeutic monoclonal antibodies. For our senior design project, we'll be using CHOK1 cells, a robust mammalian cell line, to produce these monoclonal antibodies. We are looking to grow the greatest amount of CHOK1 cells over a length of time in a seed train process. The seed train process is a process which allows cells to grow continuously in increasingly large bioreactors, all the way up to the production scale. We would like to computationally model the experimental CHOK1 cell growth data in the most accurate way possible, as well as demonstrate methods to improve the cell number by the end of the seed train. One of these methods is adding a Corning cell line bioreactor to the seed train. In doing so, our motivation is to improve the overall seed train time, thus significantly increasing the supply of antibodies and improving profit margins.
So given the initial conditions, kinetic constants, and some constraints, we developed a model consisting of multiple differential equations. These include kinetic equations such as the Monod equation and mass transfer equations. We ran this model in MATLAB and obtained results. We then extracted the raw data from MATLAB and plotted space-time yield, or STY, as well as the apparent growth rate of the cells. STY is defined by the equation at the bottom right-hand corner of this slide. Using past methods from literature works, we conducted an analysis to determine an optimal cell passaging time, T-opt, to extract the cells and place them in a larger reactor with fresh nutrients and no previous byproduct buildup. The optimal time is calculated from the given equation, and it corresponds well with the end of the exponential growth phase, before cell growth slows drastically. STY is plotted here on the left-hand side of the slide. The average of the minimum and maximum of the STY is the optimal time. So going to the next slide, we've plotted the results obtained from MATLAB. Cell density increases in an exponential manner, and so it appears linear on a logarithmic scale. And then looking at the table here, the main conclusion from this table is that when you incorporate a membrane for diffusion of nutrients and byproducts, you can see an increase or a decrease in the seed train time of roughly 5%.
Now that we've seen some results from our model solution, it's important to put our result into an economic context to determine the effectiveness of our solution. When considering the economics of our seed train, using the cell line disposable bioreactor versus a typical seed train, we will weigh the added financial benefits with the added costs. When measuring the benefits, we look to value the time to market, or how long it takes to start from a vial of CHO cells until the antibodies have been made and are ready to be sold. As you can see from the graph on the left, this process has been highlighted in red to show how long the seed train takes up of the entire antibody production process. Our seed train time is cut down by almost 5% from industry averages, resulting in an extra 2 batches that can be made per year, generating approximately $100 million in revenue. The cost of doing this are just the installation and use of the membrane, which can be seen from the figure on the right, which costs roughly $1 million. Overall, the improved seed train design will result in almost $100 million of profit, proving its economic viability.
So from our senior design project, we've learned that the membrane bioreactor is a sound replacement to the traditional bioreactor, both in terms of economics as well as cell production. A switch from a traditional bioreactor to a membrane bioreactor by a pharmaceutical company will allow for increased production of antibodies and therefore increased profits for that company. This would also impact regular people by making their antibody medicines more available to them. This result is especially important now in a time where there's a severe shortage of medical supplies. We would also like to thank our mentor, Dr. Cho, for his guidance as we completed this project. And we'd like to thank you for your attention and listening to our presentation. And we look forward to any questions that you might have.